Hey guys, my name is Rafael Avarenga and I'm a graduate researcher in the Compilers Lab at UFMG. Today, I will be discussing idempotent backward slice. First, I will provide some motivation for studying this subject. Then, I will define the problem we're trying to solve and explain the algorithm that solves this problem efficiently. Finally, I will conclude with key takeaways and resources for further exploration. Program slices were introduced by Mark Weiser in 1984. His initial motivation was to assist developers in debugging software. The concept of a program slice mirrors the mental abstraction a developer creates while debugging. When examining a specific program point, they read preceding code to identify the source of a bug. Program slices also enable code compression. By outlining functions and identifying similar ones, we can merge them to reduce code size. Additionally, program slices facilitate parallelization by helping identify independent parts of a program that can be executed concurrently. Now, let's define our problem. Given a program's control flow graph in static single assignment form, and a slice criterion, our goal is to compute all data and control dependencies backwardly. The result is an idempotent backward slice, an executable program that consistently produces an output for a given input. But what is a CFG? A control flow graph represents a program where nodes are instruction sequences and edges are code branches. The slice criterion is crucial for our problem. To compute dependencies at a program point, we must select a slice criterion. In our example, our criterion is the instruction use b2. From there, we traverse the CFG backwardly and to identify data and control dependencies. A data dependency occurs when a variable is in use, while a control dependency represents the program paths needed to reach the slice criterion using the identified data dependencies. In our case, B2 depends on B1 and so on. Our algorithm takes a program in SSA form and related representations like the dominance tree as input. The output is a slice containing only relevant instructions. The algorithm works as follows. First, we traverse the program's dominance tree, then link predicates to variables, and finally use the program dependence graph to compute all data dependencies. Let's define some key terms and execute our algorithm. We start with a C program and transform it into a CFG in SSA form. This representation ensures the single information property. That is, if the information associated with a variable is invariant along its entire life range, then we can bind this information to the variable itself. We also have five functions which determine which value definition to use based on the execution path. We also compute the dominance tree, which represents dominance relationships between nodes which with edges connecting each node to its immediate dominator. To generate our final slice, we execute our algorithm. Traverse the dominance tree to identify nodes controlling variables, link predicates to variables, and use the PDG to compute data dependencies. The PDG, or Program Dependence Graph, stores all data and control dependencies between variables in our program slice. This representation was first presented by Ferrante et al. In 1987. Given the following graph example, black solid edges represent data dependencies, while blue dotted edges show control dependencies. The PDG is computed traversing backwardly the CFG of the program. In this new graph, a node is a variable, and an edge has as its source the variable on the right-hand side and as destination the left-hand side variable of an attribution in the original program. Now, to get the output slice, we need to choose the slice criterion. In this case, it will be use B2. From that node in the dominance tree, we link predicates to variables. In this case, the predicate for B2 is W0. Knowing the linked predicates to each variable, we pass this information to our PDG. This way, we can compute data dependencies for our slice and get a simplified PDG. With this filtered PDG, we can now precisely know what instructions from our CFG must be in our new slice. We do so by traversing the instructions backwardly and respecting the constraints imposed by the PDG. At the end, the result is a program slice as an outline function and a new CFG containing only the relevant nodes and edges to calculate our slice criterion. To summarize, idempotent backward slices provides a powerful technique for analyzing and transforming programs by identifying precisely which parts of a program affect a specific computation. The algorithm we have discussed efficiently computes these slices by leveraging SSA form, dominance relationships, and program dependence graphs. This approach has significant implications for program optimization, debugging, and parallelization. By extracting only the essential components needed for a specific computation, we can open doors for advanced compiler optimizations. If you're interested in exploring this research topic further, check out the more recent implementation of this algorithm in Project Daedalus repository. You can also visit my blog for a deeper understanding of the concepts presented in this video. Thanks for watching.